The last thing that the topic that we are going to cover for ionic compounds is we're going to discuss their properties, the properties of ionic compounds. So this is the last topic, and we're going to discuss both the physical and the chemical properties of ionic compounds. Now, the first property, we're talking about a physical property, and we're going to describe the structure of ionic compounds. Now, the structure of ionic compounds, the structure is called a giant ionic lattice. So that's the structure of an ionic compound. First, the two words. The first one is it's a giant structure. Giant means that it's a very large structure. It keeps on continuing. Ionic means it's going to have ions in it, and the term lattice. There's one paper in which the definition for this term has also appeared. What lattice correctly means is it's a regular arrangement of ions. So that is what the definition of the term lattice means. So I'm going to draw a giant ionic lattice of, let's say, NaCl. Na is in group 1, it is +1, and Cl is in group 7, it is -1. So the compound that they form, it's called NaCl, or sodium chloride. Now I'm going to try and draw the ionic structure. We've drawn the dot and cross diagrams, but that's just what a dot and cross diagram describes is the arrangement of electrons. Now I'm going to be more holistic, and the structure would basically be representation of how the ions are arranged. Now in NaCl you have an Na plus 1 ion, and that Na plus 1 ion is going to, because it is positively charged, it's going to attract a Cl minus 1 ion. In return, that Cl minus 1 ion would be attracting another Na plus 1 ion. That Na plus 1 would then be attracting a Cl minus 1 ion. Then this Na plus 1 and this Cl minus 1 would be attracting each other. And this would keep on going. It's a three-dimensional structure. So let's imagine this as this diagonal line as being behind this page. So Na plus 1 would then again be attracting a Cl minus 1. This Cl minus 1 would be attracting an Na plus 1 ion. These two would be attracting each other. This Na plus 1 would be attracting a Cl minus 1. This Na plus 1 would then be attracting this Cl minus 1. And it would keep on going. This Na plus 1 would further be attracting another Cl minus 1. And similarly, this Cl minus 1 would be attracting another Na plus 1. So this Na plus 1 would be attracting another Cl minus 1. So you can well imagine that this would be a giant structure, and it would keep on continuing, and since it's a regular arrangement, it's called a lattice. So the term giant ionic lattice is the term that is used to describe the structure of an ionic compound. Similarly, we'll move on to the next property. The next property is their boiling points. Let's talk about their melting. And remember, if melting and boiling points, we're always going to discuss melting and boiling points together. So the melting and boiling points. Now, when it comes to the melting and boiling points, if you look at the structure above, the first thing is they have high melting, boiling points. And since the melting and boiling points are high, they're most likely going to exist as solids at room temperature. So they are solids at room temperature. So these are solids at room temperature. And why is the reason why they are having high melting and boiling points? The reason is, the first reason is that they have very strong, they have strong uh, electrostatic force of attraction between the ions. So the force of attractions between the ions are strong, which also means that they have strong. The electrostatic force of attraction was also called ionic. I mean, this was called ionic bonds. So they have very strong ionic bonds, and secondly, they have a giant structure, which basically means that they need to break a lot of ionic bonds to melt this. For example, to this Na plus one is stuck in its position. It's attracted by the Cl minus one. It's attracted by this Cl minus one. And it's being attracted by the Cl minus one. So to make it move around, because in liquid state it would be free to move around, so you would have to give it a lot of energy so it can overcome the force of attraction that are keeping it in its place. So that would require a lot of energy, which is why they are solids at room temperature and pressure. The next property that we're going to discuss is the solubility of ionic compounds. Now, a lot of ionic compounds are soluble in water, but not all of them are soluble, and their solubility varies. Uh, and it varies quite significantly. For example, NaCl, if you have NaCl, this is extremely soluble. It is soluble in water, and you can try dissolving. NaCl is the common table salt that you have at your home, so you can try dissolving NaCl in water, and you'll see that in one glass, probably 2 or 3 spoonfuls of NaCl will dissolve in water. But then there are certain other compounds that may not be that soluble. For example, AgCl, that's one compound, and that compound is not very soluble. It is insoluble. And the term insoluble does not mean that it does not dissolve at all. Only a very small portion would actually dissolve, the rest would remain undissolved. So solubility varies. What you can do is we're going to write down the solubility table, and it's we we have a solubility table available on our website as well. You can download the table from there, and you'll figure out which salts are soluble and which salts are not soluble. So solubility varies, but one important aspect of solubility that has to be discussed is, for example, I have NaCl, and when NaCl is dissolved in water, you're going to dissolve NaCl in water, and when it forms a solution, that solution is called NaCl aqueous. What this term aqueous EQ stands for is AQU, EOU, and S. Aqueous means a solution. So you actually have 4 states. One was solid, then you had liquid, then you had gaseous states, and this is the fourth state that you're going to study. It's called aqueous state. State means when some salt or any other substance is dissolved in water, that would mean aqueous, and you would write AQ in front of it to represent the state of the substance. So this you need to remember, aqueous state. Another thing about aqueous state is, if you remember the structure of NaCl, it was Na plus one, which was then attracted to Cl minus 1. Cl minus 1 was further attracted to Na plus 1, and this Na plus 1 was attracted to Cl minus 1, and it kept on going indefinitely until the structure finished. So it was a giant ionic lattice that it was forming. So when NaCl is dissolved in water, what you do is you first NaCl is a crystalline substance. It's in the shape of a crystal. So the first thing that you need to do is you would need to stir it in solution. What that stirring does is that it breaks all these ionic bonds. And when those ionic bonds are broken, so you have, let's say, let's imagine this as a beaker, and there's water in it. So this is a beaker full of water. When you're going to stir NaCl in this solution, the crystal would eventually break, and you would have all these ions freely roaming around. There's a Cl minus 1 and Na plus 1. So all the forces of attraction have been overcome by that stirring. But what that does is that water, when Na plus 1 breaks apart, water molecules start accumulating and they start getting attracted to the positive ion over here. So these water molecules start to surround this Cl minus 1 ion as well, because it's negatively charged. So you have all these water molecules trying to they're getting attracted to the ions that are in water now. And once these water molecules get attracted to these ions, what happens is that this Na plus 1 would no longer be able to connect with the Cl minus 1, which is over here, because there are a lot of water molecules in between, which is going to prevent that. So when NaCl, when you have NaCl and it becomes aqueous, what happens is that NaCl breaks up into Na plus 1 ions. Those are also aqueous, they're completely surrounded by water, and it breaks up into Cl minus 1 ions, and that is also completely surrounded by water. So remember this equation: whenever NaCl is aqueous, its ions are going to break apart into aqueous states, and they would not be able to join together. The only way that you can make Na plus 1 Cl minus 1 join together again is by getting rid of the water, by evaporating water. So let's try this on another compound. For example, if I have potassium chloride, and if it is aqueous, that would mean the potassium ion, which is in group 1, so it's plus 1, is going to break apart, and water molecules are going to surround it, and Cl minus 1 would also break apart, and water molecules are going to surround it, so it would be in aqueous state as well. So remember this point carefully. Whenever an ionic compound is in aqueous state, it would break down into its ions, and those ions would not be able to get back together again until and unless you get rid of water. Now we're going to discuss whether ionic compounds conduct electricity or not. So this is our next point, whether they conduct electricity or not. And if you remember the structure of ionic compounds, it was a giant ionic lattice. You had Na plus 1, it was attracted to Cl minus 1, which was attracted to another Na plus 1, and this Cl minus 1 was then attracted to another Na plus 1. This Na plus 1 was attracted to Cl minus 1, and it was forming a giant ionic structure, and you had strong force of attraction between these ions, which was keeping them in their place. Now, the first thing is we need to define what electricity is. Electricity, in it's a very rough definition of electricity is that it is the movement of charges. So electricity is the movement of charges. Now, do ionic compounds have charges? They do have charges. So because they have ions, and ions are charged particles, so they have charges. But the problem is that in solid state, when ionic compounds are solid, the ions or our charges are charged particles are stuck in position they cannot move. This Cl minus 1 cannot move around. So in your solid state, these ions are stuck in position. So ionic compounds will not conduct electricity when they are solids, because the ions or charges are particles are stuck in position. But when they are aqueous or molten state. Now, in aqueous or molten state, they are going to conduct electricity. The reason is that in aqueous or molten state, ions can freely move around. In molten state, in liquid state, your particles are very energetic and they can move around. In aqueous state, as I've described just previously, the ions are surrounded by water and they're free to move around. So, since in aqueous or molten state, ions can freely move around, they will conduct electricity. So, electricity is conducted in aqueous or molten state, but it is not conducted in solid state. Electricity would also be conducted in gaseous state, but I'm not going to talk about gaseous state because ionic compounds generally do not exist in gaseous form. So that's our fourth point. Lastly, we're going to discuss whether ionic compounds are brittle or they are malleable or ductile. What that means is that ionic compounds, they have a crystalline structure. They have a crystalline structure, which means that they form crystals, and these crystals are brittle. If you try to bend or uh, reshape them, they're going to break apart. The opposite of brittle is malleable and ductile. So these crystals cannot be reshaped or bent.